I'd like to, first of all, thank the organizers for giving me the opportunity to speak. I mean, it's really nice to be here in Barcelona. Wait a minute, I live here in Barcelona, but it's really nice to be in Barcelona. I hope everyone has had a chance to look around a bit, enjoy the nice weather, see some things. So today I'm going to talk to you about something that's a bit tangential to our work, but certainly related to our work at Qilimanjaro, and that is something I spent a lot of time with, Josephson-junction chains. So what I'm going to describe is how this device goes from can be useful in two extremes, that is as a superinductor, which maybe most people are familiar with, and superinsulator. And so I'll try to cover these things, and I suppose I can't walk around, which is, I guess I can walk. No, I can't walk around. Okay, so this is a bit difficult for me to see, but yeah, I'll get started by using fluxonium as a context for it and discuss superconductor chains, which you're probably familiar with. Move on to some internal physics of the chains and how phase slips lead to dephasing in fluxonium. And then we'll shift gears and we'll move from super-inductors to super-insulators. And I will talk about the coherent quantum phase slips, the formation of block bands, and the so-called Joule-Josephson effect. And then I'll tell you about some work I did with my group when I was a professor at UNSW that show that these super-insulating chains, chains of Josephson junctions, are actually, we believe, pinned TomonagaLuttinger modes. So, of course, we start with fluxonium. As we all know, fluxonium is a flux qubit. We used to call it RF qubit, RF squid qubit. And the particular thing about fluxonium, it's biased with a very large inductance. And so here's a circuit diagram, and it's actually, what makes this significant, or why it took some time to appear, is that it's actually difficult to get a large inductance, especially in a planar geometry, with the usual techniques. And that's because, you know, if you look at your simple undergraduate physics and you look at the inductance of a wire, of course it scales with the length of the wire, but it's sort of this mu naught over 2 pi. And if you look at mu naught over 2 pi, you see that's about 0.2 picohenries per micron. So if you want to get the large inductance needed for the fluxonium regime of a flux qubit, you need a very, 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 very long wire. And then, unfortunately, that comes with lots of parasitic modes and a bunch of things that you don't want. And so so Vladimir, building on some work I think was done by David Haviland and a number of people in another context, showed that you could actually use Josephson-junction chains and use the Josephson junction as, this was an autocorrection, as superinductors. That's what you don't pay attention, if you don't follow your autocorrect. This should be a superinductor, and one can reach 1 nanohenry per micron. And alternatively, I'd say some people are using now high kinetic inductance materials like titanium nitride, niobium, nib-tinitride. There's a bunch of different ones, usually disordered. So just to remind you about the Josephson junction, well, here's a kind of artist's conception that sort of approximates how we construct Josephson junctions. We have a bottom electrode that we deposit and oxidize, and then we put another electrode on top, and this forms a small junction that has a thickness of about a nanometer, and typical sizes, transverse sizes, of the order 100 nanometers to, I don't know, a few microns, 10 microns. This is how we draw the circuit, of course, and what is pretty well known is that under the right conditions, this Josephson junction acts like an inductor, and this inductance is referred to as the Josephson inductance. And you can see this by just taking the Josephson relations, which are the sort of semi-classical relations that Brian Josephson derived when you couple two superconductors, and you just solve this, take the derivative of this and plug it in the formula for an inductor, and you'll see that you get this object that's actually a parametric inductance. It depends upon the phase difference, and that means it's actually a nonlinear inductor. So we're all quite familiar with that. The important thing is that it acts like an inductor when you have small deviations of the phase difference, and it acts sort of like a linear circuit element only in this limit. So you have to take care of this and make sure that your circuit sort of behaves this way if you want to use this as an inductance, and there's a lot of other conditions on this. But if we want to understand the quantum physics of this device, of course, or even the dynamics, even the semi-classical dynamics, we have to include the junction capacitance here, and that becomes very important. So here's a picture of a Josephson-junction chain, a recent one from Qilimanjaro. You see, well, the usual chain of junctions. This is about 10 microns here, so you can see there's probably about 50 junctions here. I can't remember exactly the number. And in order to make, as I said, a good superinductor, you need the fabrication to be somewhat well controlled so that you have some variation in the individual Josephson energies and inductances, but you need them to be not so, to make, have a good mean value so that you can sort of get an average inductance. Because you're putting a lot in series, you can get away with a bit of fabrication in homogeneity because it kind of averages out, but you can't have wildly varying individual Josephson energies. So you need to work on this. It's doable. And, but once you get that down, you also need to when you're designing fluxonium, you need to be aware of a couple of things. And the first thing is you need to avoid the linear transmission line modes that you find in a chain, and I'll discuss this in the next slide. And you also need to choose parameters of these junctions so that quantum fluctuations of the phase difference across a particular junction are small, which means in some contexts that you don't have quantum phase slips across the junction, which we'll talk about. Now, if you go beyond fluxonium and go into the superinsulator regime, understanding and controlling phase slips is a very interesting subject, and it opens up a lot of interesting physics and possibilities I'll try to mention in this talk. So let's back up a little bit and think about transmission line modes, because if you look at this Josephson-junction array, you'll realize in a sort of very hand-waving simple picture, it's a network of inductors and capacitances. This is actually the parasitic capacitance to ground. So I'm just going to review a little bit of what happens in a very simple LC transmission line like this. If you haven't studied this before, if you've had it in electrodynamics, maybe as an undergraduate, I used to teach things like this. You write down this circuit and you do the network theory, and you realize that the eigenmodes of this form an acoustic spectrum. That is, they look like this. They sort of come from 0, which is a frequency, sort of characteristic frequency divided by the total number, and they have this kind of dispersion relation. And so if you put this in a circuit, it acts, well, like a low-pass filter. That's easy to see because if you try to excite here on the left side, then the inductor at high frequencies is very high impedance, and the capacitor is a short, so you'll see this has a characteristic cutoff frequency. But if you don't match this properly, you'll also get standing waves. And if you plot, if you do the network theory and you plot, for example, the impedance of this device as a function of frequency for, let's say, bad matching, you see these series of modes, which are these guys here. But I just want to point out in this plot that I've used a typical fluxonium junction parameters and a couple things here. You see, I think this is a chain of about 50, and you see that you get these modes that are coming down to almost below, this is 10 gigahertz here. And you also see that in an infinite chain or well-matched chain, you would have this sort of input impedance. And for a typical fluxonium chains, this impedance is actually quite high. This is actually above 30 kilo ohms. So it's way above the usual 50 ohms that you're used to dealing with, for example, in a coplanar waveguide or those sort of things. Of course, the Josephson-junction chain isn't this simple. In a very simple, low, the simplest model really that's realistic actually looks like this. You have an inductance and capacitance in parallel. You might have a series inductance of the actual island of the chain junctions, and then you have this you always have this parasitic capacitance to ground, which you can somewhat engineer by a number of methods. And if you do the network theory of this thing, you see a couple of interesting properties. You see there's actually two sets of acoustic modes, the sort of modes that pile up at the plasma frequency of the junction. the so-called plasma frequency, which is 1 over Lj Cj, the square root of that. And you see this other set of modes coming from this inductance, L0 and C0. So, and the other thing is you get a gap in the spectrum as well. So now I kind of accentuated, I used a somewhat unphysical value of L0 here. In practice, that's very, very, very small, so these upper modes are usually nothing to worry about. That's not true in some kinetic inductance materials and other things. But I just wanted to point this out because there's probably a lot of interesting things we could do with with engineering modes in these chains that we really haven't explored that are very similar to, for example, what's done in photonic lattices and so forth. The main thing here, though, is that you can't, if you want to get a large inductive bias for your fluxonium, you can't just push the number of junctions to be very, very, very large because this low mode here, or down here, I guess is a better thing, is something like the plasma frequency divided by n. So if you go to more and more and more junctions, you start having these modes that interfere with the qubits and couplers and other things you want to have. So it's important to understand these modes, and when you're engineering superinductors. The other thing that you need to be aware of if you're using superinductors is phase slips that occur in the superinductor. So we'd like to have this fluxonium where we have an inductor here, and the only tunneling of flux is across the weak junction. That's what a fluxonium qubit is. But in fact, we have, since we have a chain of junctions, we have the possibility of flux quanta tunneling through the small junction and then across one of the chain junctions. Of course, you could have just tunneling back and forth across the chain junctions. That just renormalizes the tunneling through this junction. But anyway, this is a problem, and it contributes to dephasing of fluxonium. And so the picture you would have, for example, is that if I looked in a sort of hand-waving sense at the potential and phase of an individual junction, I would have something like this. And flux tunneling, single flux tunneling, of course, takes you across the barrier here. And you can sort of get a very quick estimate of the dependence of this on your chain parameters very easily. If you know anything about tunneling, you'll know that if you want to tunnel through a barrier, the important thing is the height of the energy level you're tunneling through, which is half the plasma frequency, and the height of the barrier. And so the tunneling rate is exponential in the ratio of this to this. And if you put these numbers in, it's very easy to see that you have that the important parameter is the scaled impedance, which is the impedance, the LJ, CJ impedance of the junction divided by the so-called resistance quantum, which is 6.45 kiloohms. It's this value. And so you'll see that the actual phase slip rate is exponential in this small z parameter. And you can do a more refined calculation, which is WKB, and you'll find that this rate W actually has this form. Here's the exponential dependence of Z, and there's some other prefactors. You notice that the plasma frequency is out front. That's important. And if you know anything about tunneling over a barrier, you know this makes a lot of sense because the plasma frequency is like sort of an attempt frequency, and this exponential factor is a success that you, well, either for thermal tunneling, it'll go over the barrier, or for quantum tunneling, that you go through the barrier. So these are important parameters, and this is how you should think about quantum phase slips. And what's really interesting is that there's been a recent paper by the group at MIT Lincoln Labs where they actually studied this effect of phase slips on fluxonium dephasing. So they made a family of fluxonium devices here, where this is a superinductor. And what they did is they varied the width of these with the same overlap. And this, using this method, they were able to vary, for this family of devices, the actual scaled impedance. They use this ZA, that's just my Z that I used here for simplicity. And so what's really nice about this, and I'll discuss it later when I present our work in the super-insulating state, is this only changes the scaled impedance, but for all these different devices, the plasma frequency remains constant. So you're keeping this part constant, and you're just varying this. So it makes it makes the experiment very nicely controlled. So what they did is they made a bunch of devices, and here's the color codes for the scaled impedance. This is, of course, junction impedance divided by resistance quantum. And as the, let me see if I got that right. It's, yes, junction impedance. And what they've done is they've measured the dephasing of fluxonium. Here's at the sweet spot, and you can see as you decrease the impedance, you have really long T2 times, or dephasing times, T phi. I guess this is actually a Rabi time, and as you increase the impedance, you have more phase slips, and you actually suppress the dephasing time here. And then they plot here, of course, the data, theoretical expectations for this rate. I call this rate W for simplicity. They're in their paper, it's given this, it's denoted this way. And what's really nice here is you see it scales very well with the theoretical expectation, except maybe this outlier. And good on them for showing outliers. I think that's very good scientific practice that unfortunately a lot of people don't do. But anyway, so it's a very nice experiment, and they showed how this affects, how the superinductor dynamics, in particular phase slip, affects the coherence times of the fluxonium. And yeah, they did a very nice job of it. Now, yeah, was there something else? I thought I was going to say something else, but I can't remember what it was. Nice work. So let's just conclude then with our, so that's the Josephson-junction chain as a superinductor. And then I wanted to sort of ask if anyone is really interested in quantum engineering these. Anyone has it? Yes, I know, Oriel. So if you want to be a quantum engineer, then the kind of things you need to do in this context is you need to know a few things. And here's what I would suggest: that your chain junctions, of course, can be parameterized by Josephson energy and charging energy, or LJ/CJ, which are inverses of these. But a more practical set of parameters are the plasma frequency, square root of 1 over square root of LJ/CJ, or the square root of, let's see, square root of EJ times EC, and this scaled impedance. It's a much more better parameter set to think in terms of. And then for a given set of the plasma frequency, and we'll see this is set by the oxidation parameters, the number of, as I mentioned, the number of junctions is limited due to these internal modes. But you also need to keep this, this junction impedance below about a kiloohm or so to get long T2s. And finally, if you only, what makes it difficult is if you only have one junction process, then you have to find a way to make the chain junctions with the parameters you need and the small junction with the parameters you need for the type of qubit you're designing all at the same time. Now, if you have, if you are, can push to 2 different junction processes, it gives you a lot more freedom. Anyway, if this interests you and if you know how to optimize all these, then please send me an email. I think I might have a job for you at Qilimanjaro. We'd be happy to have people working on things. But it's not that hard. I mean, you can play around with it, and you can pin down the parameters you need. And obviously, this is not so impossible because many groups around the world have been making fluxonium. Anyway, so let's switch then to another topic. And let's see, how many minutes did I have? I have about 20 more. Okay, so right on time. Now we're going to shift gears a bit, and we're going to go from super-inductors to super-insulators. And the way we're going to do this, understand this, is by cranking up the impedance of the junctions to where tunneling of flux quanta across junctions is really enhanced. And when you do this, you'll find yourself in a completely different universe, practically speaking. So let me tell you about that universe, because it's very interesting and it has a very long history. So the picture is that, of course, and I'll kind of draw it here, is think about an extended potential profile of phase for an individual junction, just whether it's the small junction of fluxonium or the chain junction. Then I imagine I live in this washboard potential, and the tunneling of flux across the junction, flux quanta across the junction, sort of delocalizes me. If I crank up this rate W, if you remember condensed matter physics, if you learned about electrons in lattices, you know that if I have tunneling between different wells, and I think of the tight binding model, then the energy levels broaden into bands, and that's what happens presumably in a Josephson-junction. And these bands then have a certain bandwidth, which is actually in the lowest block bandwidth is this rate here. And then the picture of this completely phase is not really a good picture for the junction because it's so delocalized. What becomes a picture is quasi-charge, which is like the quasi-momentum of this system. And then, so what you do is you form bands, and the parameter here is the quasi-charge, which is a quantity that's quantum mechanically dual to the phase, and it's really the charge that's gone through the junctions. So what happens is charge becomes localized on the junction capacitance, and that's parameterized by this quasi-charge. And so what happens practically, or in principle, is that you go from a device that has a sort of nonlinear inductance to a device that has a nonlinear so-called block capacitance. And in principle, and I keep saying in principle because this is actually not completely settled experimentally, and there's a lot of controversy that's resurfaced in the last few years, but in principle, you would have, instead of the Josephson relations that we're familiar with, you would have these dual Josephson relations, and what would happen is you would have, instead of a critical current, you would have a critical voltage, and then you would have, once that's exceeded, you would have some, you would have not flux progressing to give you a voltage, but you would have charge progressing to give you a current. So that's the picture. And so just in terms of a plot, it would look something like this. Here's the usual Josephson effect. We have a critical current, and then once we exceed that, we start developing a voltage, and then you have these Josephson relations that I mentioned. For the dual Josephson effect, you would sort of flip voltage with current, and you would have a critical voltage, and presumably these dual Josephson relations. This is actually data from a chain, and you can see that this is a really hard voltage gap. In fact, if you go to measure that in some of our devices, you get something like gigaohms. But anyway, what's so interesting about this, apart from making interesting quantum devices, is that this would enable a primary current standard, which, in addition to the usual voltage standard that's used now to define the SI units. So, you know, if you could do this, this would be probably as significant as the Josephson effect itself. And I'll just mention about the primary current standard. If you're not aware of it, then what happens in the Josephson, the AC Josephson effect, if you shine microwaves on this junction, what happens is you alias this very sharp zero voltage step into other steps occurring at some prescribed voltage, which is basically proportional to the frequency. This is the flux quanta. So you're sort of synchronizing flux quanta across the junction, and you have these different steps, and these things are extremely accurate. They give an extremely relation between frequency, and frequency is very well measured because we have atomic clocks, and voltage. So this, and the only two constants involved are h and 2e. So the accuracy of this primary standard is related to the inverse slope of these steps here. So if I want this accurate to 10 to the minus 12, which I think is what the voltage standard is, or probably it's even more, it's sort of like 1 over this slope is what you need to achieve. So are people familiar with the voltage standard? Maybe some people. Anyway, this took a number of years to do, but it's done in many labs across the world. In fact, my old postdoc is now in Sweden doing these sort of things and doing quantum Hall standards and I think. Anyway, that's the main deal, but of course, this comes with a whole bunch of coconuts and bananas. Caveats and possibilities. Sorry, that's an inside Qilimanjaro joke. I couldn't resist. So, and what I'm trying to say is people have been wanting to achieve this for since it was written down. And so how does that go? Well, this dual Josephson effect has a very long history. It started out in about 1980, in the early 80s, and there's a really interesting set of papers by Whiteham and Clark from Sussex. I was talking with Paul about this the other night. I discovered this not too long ago, and it's amazing. If you dive into these papers, you'll find the flux qubit Hamiltonian buried in there. But, and of course, Licker and Zorin wrote a number of papers describing this. And so there's been this decades-long effort to produce dual Shapiro steps. So these guys are called Shapiro steps for the guy who discovered them. And to do them in a dual Josephson effect, there's been, well, people have been trying to do this since the 80s. But more recently, people are looking at this again, and they realize that trying to understand this, or so-called coherent quantum phase slips, as it's fashionable to say now, they challenge the standard circuit QED model of circuit quantization. There's a really nice paper on this. I wanted to talk about this, but some of these things, but I won't have time on this. But you can look at this and look at the references. And to do this with a single junction is really difficult because you need a high impedance junction embedded into a high impedance environment. So just some point here, a high impedance junction is in itself not a coherent quantum phase slip element. You have to put it in a high impedance environment. That's really hard to do. And it's hard to delocalize the phase because, you know, what you need to do is delocalize this phase across the junction. And it turns out not only is that hard to do, but it's also become a bit controversial lately. And there's a really nice paper that came out a couple of years ago by Michel Deveray. Sorry, I didn't put if you search on this, you'll find it, but I didn't put the reference. But the title is, Does Brian Josephson's gauge invariant phase difference live on a line or a circle? And this is really interesting, and I would suggest you read this. It's a very well-written, kind of colloquial style paper. Anyway, the message is, however, that a robust coherent quantum phase slip element or dual Josephson effect device would not only would it produce this current standard, but it would open up a lot of possibilities for novel devices like gate tunable flux qubits and couplers, topologically protected qubits, quantum sensors, novel quantum emulators. Some of these are mentioned in this paper here. So, you know, a lot of people have been working on this. A lot of good academic careers have been ruined working on this. And I just want to show you some of the things that show why it's hard. And I guess I am now about 10 minutes to go. But so I don't want to go in details about this, but I'll just show you an illustration of the efforts people have had to make to try to do this in a single junction. So here's a recent paper where they tried to bias this weak link, not a single junction, but a weak link, in a high impedance environment. And you can see they have two sets of inductors, very big linear inductors, a 4-point measurement with resistors, and then they have their junction over here, and you have to go through all of this to try to get current steps, and they shine microbes on it. And you can see, well, there's some things there, but remember the accuracy is something like the slope of the step, and it's not really a slope here. So as a current standard, it's not great, let's say. There's another device here where there's a junction also embedded into a bunch of inductors using high kinetics inductance materials, titanium oxide, and so forth. These authors chose to present the axis flipped from these guys, but once again, the step flatness would give you the accuracy as a current source, and you can see it's not great. And so there's some progress that's been made because there were experiments done on these systems back, I mean, not long after I was a postdoc, long before I was a postdoc in Chalmers, and, you know, things haven't progressed. Things have progressed, but not, I would say, hugely in a single junction thing. So anyway, it's hard. There's another really interesting recent paper, though, that I really like, and I got to tell you, I'm not going to go into details about it, but I got to tell you a story about it because about 8 years ago, I was giving a version of this talk, and there's this guy, Niccolo Cressini, this was at a workshop in the very north of Sweden, like, I don't know, way up there. And this PhD student, Nicola, was there, and he came to my talk, and he asked a few questions. And, you know, about 5 years later, I get this email saying, oh, here's this draft I have with these current steps, and I did this, and what do you think about it? And I nearly fell out of my chair, you know. But there's still a lot to understand. But what's really cool about this paper is they biased a single junction inside of a chain. So this is kind of like fluxonium, except the ends are open. And they drove it with the internal modes that I discussed at the beginning of the talk. And they were able to see these current steps here. But the details of understanding how this occurs is still very murky. And I think they're still struggling with the understanding and engineering this a bit better. But it was pretty neat. So maybe someone here will go off and do, you know, really improve this. I don't know. So anyway, one more thing I want to mention about biasing a single junction then, and I'll be really quick now because I'm really running out of time. So there's a recent result called blockonium where they make fluxonium with a high inductive bias, and once again, this is not easy to do either, and what they had to do to reduce the parasitic modes that come from capacitance between these two chains, this is their fluxonium, this is their fluxonium superinductor, is they were able to suspend this superinductor to to reduce the parasitic capacitances and allow them to go up to very large numbers of junctions and a really large bias inductance. And here's the kind of phase diagram that shows where they are relative to the usual fluxonium. And what these contours show is that even with this extreme, the percentage of the phase being not in between minus pi and plus pi is only 40%. So if they calculate the phase profile for what their device should, I mean, you can't measure this, but you can see it's only delocalized into a few wells. So it's very difficult. So now I have to move. So, you know, what you'd like then, if you wanted a CQP, a coherent quantum phase slip element, is you would like something that has a critical voltage that scales with length, because the single junction is going to be tiny and it's going to not be very useful. You want a circuit element that you can insert like at will into some device. And probably the single junction, I would say probably is not the solution. I say probably because I'd never say never these days. And so what is the solution? Well, the strongest candidates are super-insulating Josephson-junction chains and super-insulating nanowires. And this is what people are working on today, and there's a number of groups trying to go in this direction. And what's interesting, just from a theoretical perspective, is this transition to the insulating state becomes a phase transition rather than a crossover. So it's kind of more robust or harder. Well, it's thought to be harder, and that means this device would be something you could stick into a circuit. You know, you wouldn't have to worry about you know, all these inductors and resistors and everything that you have to, all this, you know, baggage that you have to use, because the device itself kind of provides its own inductive environment, more or less. So that brings me to then our superinsulating work. We at UNSW, starting with a lab that was empty in about 2011 and running about 6 years, we fabricated a whole bunch of Josephson-junction chains, and these are our superinsulating chains. They're a little bit different than fluxonium because you can see, if you know anything about fabrication, the evaporation angle was this way instead of the plane of evaporation was vertical instead of horizontal. There's some reasons for that I could go into. It makes better large impedance junctions, but the point is, we were able to vary the area by dose. We were able to change the plasma frequency by oxidation parameters, and here's some examples. But we were able to basically quantitatively study the critical voltage in a bunch of devices with lots of varying parameters. And the way we did this was because at first we didn't know what we were doing. Actually, we didn't have a theory. We just knew we had all these devices with different parameters, and we had measurements of this critical voltage, very, you know, sharp onset of the current. And at some point, I got the idea to scale the critical current by the number or by the number of junctions and the plasma frequency, scale both the QPS, expected QPS rate, by a plasma frequency and make these dimensionless scaled variables. Now, and so what happens if you do this in this simple model, and this is I call it's an independent quantum phase slip model or quasi-charge model, then you get a sort of trivial, you get this relation for this scaled critical voltage with scaled block bandwidth, which is, related to the junction parameters you can independently measure. You get, yeah. Okay, you get very simple exercise. So why would you do this? Well, because it's fun, because I did a PhD in statistical physics, so I'm brainwashed into looking for scaled variables. I guess there's some truth to that, but no, because we had all these devices that we wanted to put on the same plot. And what we'll see, more importantly, is that this independent, what I call rigid quasi-charge model, doesn't work. And understanding, especially this exponent here, is the key to understanding what's happening. So, and I'm running out of time, so I'll just tell you that we became aware of some work by Sasha Sneerman and Nicholas Vogt at Karlsruhe, and they said, let's just back up and think about classical. We know that there's offset charges. We know there's disorder. Let's just classically see what we get. And they went through this interesting model that has to do with pinning of elastic systems. It comes up in lots of different places. And they were able to work out this classical model, and it gives, instead of an exponent of 1 for this scaling law, it gives an exponent of 4/3. And so off we went, and we made a bunch of different devices, and we varied the plasma frequency, and we varied the number of junctions, and we varied EJ over EC, and the impedance, and all kinds of things. And we used this scaling relation, and all the data fell on this plot, but it wasn't the alpha equals 1 plot. It wasn't the alpha equals 4/3 plot, except maybe up here. It was some other line, and we scratched our heads for several months, and I went to Karlsruhe, and I talked with Sasha Sneerman until, we talked with some people that knew localization theory, and at some point we realized there was some quantum physics that we couldn't leave out. And the quantum physics was that these chains are actually implementations of a TomonagaLuttinger mode. And this depinning theory still works, but this localization length, which is the key, sorry I missed this, this is the key to understanding the depinning transition, because the critical voltage is inversely proportional to the square of that. That still holds, but this exponent alpha is not a constant anymore. It depends upon some impedance of your arrays, and you have this sort of running alpha that depends upon how close you are to this transition where k equals 3/2. So k is this lettering, it's your constant. It's just like the electromagnetic screening length, inverse of that times this scaled impedance that I told you about before. So anyway, and there's a lot of theory behind this. That was a kind of big move, and finally we realized, well, yeah, we think this is what happens. And if you don't know about TomonagaLuttinger physics, there's a really big book by Terry Gianmarchi on this. There is a universality in description of quantum physics in one dimension, and so almost everything can be described in terms of this TL modes. And this connection between that and Josephson-junction arrays had been explored a little bit, but not really experimentally. So, and I'll just show you that then, and I'll conclude. I think that was a really key thing for my own understanding, because it told us that super insulating Josephson-junction chains are pinned TomonagaLuttinger modes, and that this critical voltage comes because of, from this quantum mechanically enhanced localization length. And, you can still, if you want, interpret this as QPS, but the main point, well, I'll come to that in a minute, it has some implications that it's not what people thought was happening at the superconductor-insulator transition. In fact, for decades, you see this term in the literature, and it's a bit ambiguous. And I think what people don't realize is what they thought was superconductor-insulator was really superfluid Mott insulator type of physics, but what we observe, what the signature we see is it's actually superfluid Bose glass. And what's important about that is you can look at the theory, and you can see that the expectation over disorder, or a large number of junctions, this correlator goes to 0, and this is exactly what you need to have a dual Josephson effect. So sadly, no dual Josephson relation, no Shapiro steps, and it doesn't look good for this at first sight, but we did match some theory, and And what we've learned is that somehow we need to reduce the offset charge. And the good news is I've kind of been thinking about this since this work was done, and I'm almost convinced that we don't need to completely banish offset charge, which would be very difficult. We just get away from maximal offset charge, which means that your potential on your island goes from across the whole range of plus E to minus E. And maybe there's some interesting differences in using nanowires, and I'm still working myself to try to understand that. So if you want to know more about TomonagaLuttinger liquids, we just came out with this review article, and it's in Nature Review Physics, and it basically shows how the universality of this description in a number of different systems. So that's it. I know that was a lot. Happy to answer questions, and thanks again for listening.
So we have time for some questions. Yeah, at the front.
So there are two approaches. One is using junction, and one is using nanowire. And which one do you think is better?
I think they're equally bad. No, I don't know. I come and go on this because, and unfortunately, I didn't have time to show you. There is some recent work with nanowires, and so the pros of nanowires are. The problem we have here is because we have this random offset charge, which I know you're very aware of because you worked on charge qubits for such a long time. And so that's a kind of characteristic of having islands, or that's something that comes with having islands. And nanowires, I mean, they have kind of islands that are very strongly coupled, they're very disordered, but you don't really have, you may not have the same kind of offset charge problems. Then again, you have disorder in other channels in the nanowires, so it's not clear to me what happens. So I don't know. I don't have an answer to that question. Probably we need to pursue both and understand the physics of nanowires a lot better.
I have a question.
Okay.
So you showed in your towards the end of your talk that because of this TomonagaLuttinger physics, you don't get Shapiro steps. Earlier on, you showed.
No. Okay.
Earlier on, you showed there are Shapiro steps.
Yes. Yeah. Well,
how do I square this circle?
Okay. So we tried a lot, but that's another point. So if it's a pinned Luttinger glass state, then you probably can't synchronize the charge because even though it's insulating, you push charge in and it just kind of rearranges the offset thing. So imagine just hand waving, I just can't synchronize the charge through there. Yeah. So, but if you could get to this Mott insulator state, that doesn't happen. This is not zero. And so that's what you need to do. And so you need to do that by somehow reducing disorder. I mean, there's some theory I could discuss with you about that, but maybe there's a way to do it, but we haven't figured it out yet. I would like to think there might be a circuit way to do it, but I haven't figured that out. So.
But your suggestion, therefore, is that the Krishini experiment is in this Mott insulator regime?
No, they're biasing a single junction with a inductive bias inside an array. So they're more to the, they're more like the original stuff of a single junction. So their physics, the insulating physics is combined. The array is just using a bias and a drive that's using the internal mode. So it's very different. So the gap, the voltage gap in that will never be very, very big, and probably the current you can drive is probably not going to be big. But it's very different physics.
Understood. Time for another question? If not, let's thank Tim again. Very nice presentation. Thank you very much.